Okay, now we're going to have a look at the surface area of a sphere. So this here is this is another way of thinking of the surface area of a sphere here. It's also detailed in the textbook. I'm going to try to explain this here. So imagine that we have a sphere here with a thin skin. Okay, so I'm going to say that the thickness of the skin here, I'm going to call the thickness of the skin here T. So there's T here, and the radius of the sphere is R. So there's a sphere with radius R. And we have a thickness here, we have a skin of thickness T here. So I'd like to determine the volume of the skin. Now, if the skin has a thickness T all the way around, this means that the outer surface of this sphere, the sphere encased in its skin here, is going to be a new sphere with radius R plus T. And since the original sphere has radius R, the volume of the skin should just simply be the difference between the two spheres here. Which means that the volume of the skin is going to be, in this case here, it's going to be 4/3 pi times R plus T cubed minus the volume of the inner sphere, which is 4/3 pi R cubed. Okay, so we're going to go ahead and do this here, and this we're going to have to do a little bit of algebra for. That's okay. So it's going to be 4/3 pi times, now let's see, R plus T cubed. You can do this here, do this on your own, just a little bit of algebraic practice for you. You can share R cubed plus 3R squared T plus 3RT squared plus T cubed. And now notice I'm factoring out a 4/3 pi here, so I'm left with an R cubed on the inside. So note the R cubes dropped out, which is very nice. So we get 4/3 pi times 3R squared T plus 3RT squared plus T cubed, right? Now I can go ahead and distribute this in here and multiply this out. The 3 cancels out with this 3 over here, leaving me a 4 pi R squared T. And then this 3 drops out here, we're left with 4 pi RT squared, and then of course we're going to have this 4/3 pi T cubed. So this is going to be the volume of the skin. Now, another way to think of the volume of the skin is that if we look at a very magnified area of the sphere here, this is basically, if you think about it, it's going to look, we're going to have some sort of fragment like this here, right? And in this local area, the fragment of the skin looks basically like it's basically the outer area times the thickness of the skin here. So this here is our T, and this is the outer area here, right? This sort of blue thing on the top is the outer area of the sphere here. So one way we can think about this is that this outer area is going to be the surface area of the sphere here. So I'm going to write this as the surface area, I'll call this SA, times the thickness of the skin T. Because the skin is the same thickness all the way around, this T is going to be consistent here. So that means the volume of the skin should also be this outer surface area times T. Okay, so we got that there. Fine. Now I'm going to go ahead and divide everything by T here. Get rid of the T and everything. So that means our surface area here should be equal to, let's see, the nice part about this is that there's a T everywhere here. This T cancels the 4 pi R squared T term, so we have 4 pi R squared. This T knocks this power down 1, so it becomes 4 pi RT. And then this becomes 4/3 pi T squared, because again, the T gets knocked down a power. So our surface area should be equal to this. Now, of course, this doesn't look very good, but let's think of it this way. If you feel a little bit uncomfortable about this, you should, because, well, this isn't, like I said, this works for very small areas here, right? If we want this to work here, if the thickness of the skin T is particularly big, then this is not going to be, it's not going to be a perfect prism here if we were to unfold the skin and, unwrap it nice and flat here. But as T gets really thin, this, the thickness becomes less and less relevant here. The thickness becomes almost irrelevant here. So as T gets very small, the thickness, this thing should approach just the surface area of the sphere here. Which means that in this case, we want to see what happens as T gets really small. We want T to head to 0. Now, in calculus, this is known as a limit here, but I'm going to do this anyway. We're going to have T approach 0. So as T approaches 0 here, note that as T gets closer and closer to 0, this thing doesn't have a T in it, so it doesn't care. It doesn't care that T is shrinking. It just stays, it's just happy as it is. However, this is a T in it. Notice as T goes to 0, that means this T going to 0 means that this quantity, 4 pi R, is being multiplied by a very small thing here. So that means this is going to tend to 0. Similarly, t squared, this actually gets this is even worse here, because you have a t squared term here. As t goes to 0, this rushes even more to 0 here. So you have 4/3 pi is powerless to keep it in check, and this is going to approach 0 as well. So as t approaches 0, this term goes to 0, this term goes to 0. Which means that as t gets very, very close to 0, that means our approximation of the surface area gets much, much better. This goes to 0, this goes to 0, and the only thing that's left is 4 pi r squared, because this becomes 0 and this becomes 0. So the surface area of a sphere is therefore 4 pi r squared.